Okay, so we're still talking about charged particles and their movement through electric fields. And in the first part of the lesson, we talked about basically moving through uh, um, the electric field of a point charge and we looked at some of the problems that were associated there. But electric fields that are created by point charges, well, that's only one type of electric field. There's lots of other types of electric fields. And the other one specific kind that we're going to talk about in this course is what's known as the uniform electric field. And it's the type of electric field, if you'll recall, that we get from a parallel plate. So we've got one plate here that's charged up, positive, and we get one plate here that's charged up, negative. And so if we recall in lesson number 3, which is all about electric fields, it actually wasn't a lesson number 3, it was lesson number 5, that was all about kind of electric fields, or lesson 4, I think. Anyways, we saw that, oh yeah, this is just uniform, right? It's a uniform electric field. It's the same all the way throughout. No matter how close you are, no matter how far you are, it's a uniform electric field. This is going to be very, very helpful, okay? Because basically this is what it looks like. And what we're going to be able to do is we're going to be able to say that the work that's done on any particle that's placed in here, any charged particle that's moving through this type of electric field, is just the electric force on that particle times however far it moves. And so there's lots of course, what's the electric force? Well, the electric force is the charge times the E field. And this E field is going to be just a number. It's going to be like 5 newtons per coulomb. It doesn't change how far or close you are away. It's basically always the same. So one of the things, this is just a little aside, but basically when a test charge travels through a uniform electric field, like this, see here's a test charge, and it's traveling through this electric field. Its motion, its path is bent, okay? Because this experiences a uniform force, it experiences a uniform acceleration. And so for this type of electric field only, we can use our standard equations of motion, our kinematics equations. And that's going to be very, very helpful, because as it turns out, in science and in technology, parallel plates are actually used quite a bit. Okay? So don't worry about how complex this is, but what you should notice is this type of motion, this blue line that's kind of curving here, looks a lot like a projectile. And that's definitely what this is. Okay, so these are projectile motion questions when a charge is moving through an electric field. Okay, so here we have that the electric force is equal to m times a. This is Newton's second law for what's acting on this particle right here. We know that the electric force can be written as the electric field times the charge on this particle. So here's the electric field, here's the particle, and this is the force. Very nicely, this can be written as the acceleration of this guy is going to be the electric field times the charge divided by m. This is only for one of these types of fields, and that's why I divided this lesson up into 3 parts, just to make that a little bit more concrete. All right, so here's example 2. The potential difference between 2 parallel plates is 8,000 volts. If a free electron is released at the negative plate, with what speed will it hit the positive plate? So we have lots of tools at our fingertips in order to solve a question like this. And one of the ways that we're going to do that, one of the reasons why this is difficult, is because we say, oh my goodness, what tools are we going to extract out to use to solve? Well, let's list what we have. We know the potential difference is 8,000 volts. We know what the charge of the test charge is. It's minus 1.6 times 10 to the minus coulombs, no, minus 19 coulombs. And we know the mass that's on one electron, because that's what our charge is. Our test charge in this case is a free electron, 9.1 times 10 to the negative 31 kilograms. With what speed will it hit the positive plate? Well, we know that the difference in potential energy is equal to Q times the potential difference. Well, we know what the potential difference between the plates are, and we know what the charge on the free electron is, so we can figure out the electric potential energy from one side to the other. Here it is, negative 1.28 times 10 to the negative 15 joules. It means that this much energy can be given up to the speed of the electron. And that's exactly what we're going to do. We're going to say, oh, here's the potential energy. We're going to turn it into kinetic energy. And of course, that's exactly what happens. The negative and the negative will cancel to give us a positive. We know it was released from rest. We can make our substitution for mass. We can take the square root, and we get 5.3 times 10 to the 7 meters per second. Now, we would know if it was more than 3.0 times 10 to the 8th, we might have a problem, because that would mean the electron's moving faster than the speed of light, which is not possible. But this, in fact, is safe, and so we're okay. Again, we're going to do lots more problems like this, where we've got parallel plates, and we've got things that are moving in between those. So that's another type of problem that we're going to see. And that's it for section 2, or part B of this lesson.